Okay, much of the math that we'll be dealing with later on in the discussion of solving for and inverting problems to solve for tensor elements is going to be constructed around an architecture that involves vectorization and Kronecker products. I think that a good starting place is just considering linear optics and vector properties, and then we'll work our way up to tensors systematically. So a vector is formally a rank 1 tensor, the tensor being the most general term for all of these vectors, matrices, and so forth. So let's consider a case where we're describing a vector that would be in 3D space, and we want to describe that vector in two different reference frames. We're initially starting out in an old reference frame, and then we're asking what would that same vector be in the new reference frame. Old being down here, and we're just going to look at the current case of azimuthal rotations. We're rotating about z by this angle phi. And so in that case, z is unchanged, and if you ask what is the projection of the x component of this red vector onto the new coordinate system, then you're really projecting x old onto x new, and x old onto y new, and vice versa for y old. And so you can see here the projection of x onto the new y coordinate is going to have a negative sign, and then the projection of the x onto the new x coordinate will have a positive cosine term. So just by these simple projections, you can convince yourself this should be the appropriate rotation matrix to convert from the old to the new. Now, with that being said, if you look up in Wikipedia or look up in several textbooks, you will find a variety of different rotation matrices, and they all differ based on how you're interpreting or viewing the operation. In this case, we are really thinking in terms of an external rotation. So this is in an external fixed new reference frame, and so that's why we end up with this particular set of rotation operations. Okay, so that gives us a toolkit for transforming and describing a vector in two different reference frames, an old and a new, which differ by this azimuthal rotation. How do we do the same thing for a matrix? Well, this is a classic trick. And the classic way of doing this is to rotate your own reference frame from the new to the old, and then rotate back to the new reference frame. This combination will then give you a new representation for your alpha matrix. So it's a simple coordinate transformation into local, and then into old, and then back out to new. So for 3D rotation, three-dimensional objects rotation for a matrix, then it's sort of a sandwich architecture for the rotation matrix being on either side of the transformed matrix. For tensors, it turns out there is an analog of this same operation. So we can rotate into the reference frame of the old beta, if beta is a 3 by 3 by 3 tensor, and then rotate back out into the new reference frame by a direct analogy with what's going on with linear optics. To point out the double dot is going to indicate, it's not always two objects to the right, but it's going to indicate a tensor product in the order this one first, then this one, in terms of the indices of the tensor. So a tensor will have two sets of inputs and one output in this case, as shown here, and that's how they are arranged as such. Hopefully that makes sense, or if it doesn't, don't worry, it'll hopefully make more sense later on. Okay, we do a lot with vectorization, and you'll see why hopefully shortly. How do you vectorize a matrix? Vectorizing a vector is pretty easy, so we won't bother with that one. But if we vectorize a matrix, the classic way of doing it, if your matrix is alpha x, alpha x, y, alpha x, z, alpha y, x, alpha z, x, boy, you really can't read that, that's supposed to be an alpha, so forth. Then the first entry corresponds to this one, the second entry to that one, and you do column-wise sets of elements, and you stack them into one long vector as opposed to a matrix. So that's the general architecture for the vec operation. We'll actually introduce an alternative form, and the rationale for doing so is not obvious for matrices, but will really help clarify things when we get to tensors, where the bookkeeping gets to be a lot more hairy. And in here, we're introducing this ascending vectorization form, which is in the case of a matrix, is just the vectorization of the transpose. And if you transpose, what happens is that you now are grouping this way with your elements instead of column-wise. And the big advantage is that you end up with tensor elements that appear in alphabetical order of indices. So XXX, XXY, XXZ, YX, so this is all in alphabetical order. The advantage here is that no matter how these tensor elements start out, if they're in ascending order, we know exactly where each element is. And of course with matrices, that's not that big of a deal, but when we get to tensors, it will turn out to be highly advantageous. So we've explored one way of rotating a matrix, and that's through this sandwich architecture where we rotate by one inverse matrix and then let it perform what the alpha do its thing, if you will, and then rotate back out to the new reference frame. There is another equivalent way of doing the very same operation. I want to introduce that here using the vectorized notation because it'll have it directly transfers also over to nonlinear optics. And in this case, we're taking advantage of a symmetry relationship shown right here. That if you have, in this case, we have R, alpha, and R. If we have three, and actually this would be R negative phi and phi, right? So we have these three matrices, and if we want to rewrite it in an ascending form for the middle term, which in this case is alpha, then we can rearrange this in this, taking advantage of this symmetry relationship, such that we have the transpose of R negative 1 in this position. And going back here, the transpose of R negative 1 turns out to be just R of phi. And you can sort of see that from the form of R here as well. The key is that R turns out to be a square matrix, and so therefore the transpose and the inverse are equivalent. But here, if you were to transpose this, then the sign would just invert. You would also get the exact same thing if you put in negative phi instead of phi. So that's why those rotation matrices, the transpose of a rotation about negative phi just recovers the rotation matrix itself. So now we have a way of taking all 9 elements in the matrix, vectorizing them, and then multiplying them by a 9 by 9 created by these rotation matrices to make the vectorized form of the new matrix, which we could always then unvectorize if we wanted it to be in matrix notation instead. But this is an alternative and equivalent way of doing the rotation operation for a vector, or for a matrix rather. Now the big kickoff, the big advantage is really when you go to tensors, because the bookkeeping starts to be quite tedious. And there's a lot of things that we can do with the vectorized form that we can't easily or conveniently do with the tensor left in the tensor notation. So if we can vectorize it, then if we have, again, a situation initially defined like this and apply the appropriate identity relationship, we can rearrange this where we bring these over in transposed forms and vectorize each of these two. When you transpose the inverse, again, we're right back to our original rotation matrix, which is where we get that expression. So the advantage here is that if we know something, if we have the beta tensor written in one coordinate system and we want to describe it in a new coordinate system, we can vectorize and then just multiply by this Kronecker product of rotation matrices to do that transformation. So it's fairly straightforward. I'll end with just a short summary of some really useful identity relationships that connect both matrices and tensors for vectorization operations. I'm not going to go through the list though, but you can just pause this and study them to your heart's content on your own time.